So today we with Armands will tell you about thank you. I'll try to remember. We'll tell you about our journey, how we developed our graphical engines in evolution. Yeah, let's start. At the beginning, Armands will introduce the company, and then we'll get a bit more in technical details, but no worries, I will not ask any questions later. No need to remember it.
Hello everyone. So, just a little bit, what is evolution, just to better understand why we decided to have this decisions what we have. So, evolution is not a casino. So, some people think we are a casino. No, we are like developing solutions for online casino. So we are creating just software, hardware, studios, everything, and then just sell to the game operators and take a fee for that. So, in short, we just create games. What we will cover, we will show our journey and experience, how we from zero to have some kind of internal in-house rendering engine, and overall experience, why we did that, what kind of decisions we did have, and like overall experience what we have in this journey. Just a small off topic to better understand the talk. I want to show you what kind of games do we have. We have a multiple type of games, but in this talk you have to just know two. So first is live games, which is our main category. These are the games where we have real live studio with real live presenters, and we have like a game overlay on top of the video from the studio. And the first person games are games which are like there's no studio. Everything is rendered on the client side in the browser with 3D models and so on. So this is how it looks in the live game. So there's a stream from the game, from the studio, and over the game we show some kind of game components. And the first person game is like fully 3D world on the browser, single player, you decide when to bet, how to bet, and so on. So, decision started 5 years ago, and what's the current status of 3D world in evolution? So we have these first-person games. We understood how to create them, and we had stable architecture how to build them. But for live games, we did have like possibilities to add this kind of I don't know 3D elements or very rich animations for the live games. For live games, we had like very hard code UI and animations, but yeah, so we wanted the business wanted cool animations. They wanted maybe we can create some like mini games inside the live games with 3D models. So this is how like the idea was like born. That hey, we need to think how we can make like use 3D in live games. So. This also will give a better, for the designer department, better solutions and some ideas how to make our games better. So here's like a small video how the first-person games looks, and we needed some of the features inside the live games. So yeah, it's very rich. Everything is 3D models. This is screen like recorded from the game itself. This is how it looks inside of the game. And this is how the player plays. So, yeah, hard stuff to be getting live games, and yeah, so we had a big I don't know, investigation and work to get it running on the live games. So now I will ask Uldis to join and talk a little bit more about the frameworks itself and how we like it grow further. Yeah.
Well, so before we start, I'm just curious, how many of you have heard before or done any 3D browser games or any other 3D games in their careers? Okay, quite many hands, because if you take statistics that in browser 3D is almost niche, so you have some gaming areas, but mainly it's for, if you take globally, the statistic will be approximately 20 or even less % of web pages use some sort of 3D, and that includes also the shops with just previews. And so I'll give a very quick introduction, so at least that we all are on the same page about what we are speaking. So if you want to have 3D graphics in a browser, you basically need to use WebGL at the moment. There is second generation called WebGPU, but let's leave it out. This is the newest API that is rapidly taking place, but at that time when we were starting, we had WebGL 1 basically. We had WebGL 2 supported, but only on very few devices. And the trickiest part is the technology is there in the browser, you can use it, but it doesn't mean it will work. Because, yeah, you can have some hello world applications there on some devices, but that's basically it. So, yeah. That's why you need to be a bit smart when it comes. Yeah, so very quickly, maybe some keywords, what I will probably mention quite often in this talk, so you understand about what we are speaking. In 3D world, you have three main keywords. That's mesh. That's basically, in easy words, it's just an object what you see on the screen. It can be a, I don't know, plane, shape. It can be a circle, whatever. It's just a container, similar as you would have div, no? So that's mesh. So it's just abstract unit what you use for hierarchy. Shaders are C-like code executed on graphic cards, and they are used for transforming. So in two words, they define where you are located on the screen and how you look like. So, for example, if you will take this screen, you will see a lot of 5 pixels for the text. So each pixel is basically rendered by the shader code. And there it's very fast code to execute, but it has a lot of limitations. It has no memory, for example. So all you do on shaders, you do only for one specific point on the screen. And program material is just a name what usually frameworks add to describe shaders. So because there are like native APIs in WebGL, and then you have your own objects what you operate in your game. So just in case if these words are used, you probably will understand a bit more now. Okay, let's start. So as Armand showed, we had at that point we had finalized our first-person games. They were running, everyone was happy, most of the part, and then business decided, okay, let's add this also to maybe our live games. But there's a catch. First-person games, we are deciding which devices we are supporting. In live games, we have very, very low entry point. So at that time, we even had this guy in the room called Internet Explorer 11. For these who are born a bit later, this was the de facto browser for a long time. But it worked. You could run web pages there, yes. That's it. But yeah, this was a requirement. So that's of course meant that our direct experience from first-person gaming will not be available there because we didn't support Explorer 11 with our first-person games. Also, we have very strict rules for loading, as our colleague in previous talk already mentioned. People are not ready to wait for you for 10 minutes or more. So we have very strict rules about how many seconds the player will wait. So it means that all our live games have threshold, so they need to load in X seconds. And yeah, that means that no big frameworks. It means that we cannot just take any ready framework like we did in first-person games, Babylon.js, for example, or 3.js. These are the two most common ones. So at that time we realized that, yeah, okay, maybe it will not be as easy as it looks like. And also, yeah, as we have clients all over the world, so not everyone has the nicest and newest phone in their hands or even tablet. So we need to support devices that basically are capable of maybe opening emails and reading news. That's also a thing. Okay, then how we started. So we dropped immediately all the heavy libraries because at that time, the situation is better now a bit, but at that time, for example, Babylon was about 1 megabyte of engine alone, so it's no way. So our games are way smaller than that. So also we decided that we will try to make our code generated, so we will try to avoid big assets where possible, but we will touch that topic a bit later. And we also tried to reduce quality. This was a tricky point because our design department, of course, sees these AAA games, what they're running on their mega computers, and then they of course wanted the same quality in the browser. So this is a very tricky part when you work with people nowadays, because if you can play a AAA game on your phone, they expect that you can do the same in the browser. It's not the case, because firstly the API, the WebGL, is very, very old. So only a very small amount of features are available there. So it's one of the first generations of what you can do on your native apps, or let's say on the same phone even. And also other big issue is security. So because your browser is executing code on your machine, so all the code what is running in WebGL is not run directly in GPU, but through sandboxes. So that also makes it much slower. So what we came up with that, let's see. So at first we wanted to make everything from scratch, but as there was like time limit, so we could not experiment forever. I was making some workshops for raw WebGL at that time, so we thought maybe we could do it, but no. So we found this OGL framework. This is not really a framework, it's a library that wraps WebGL code and makes just things easier. So basically, if you will write a minimalistic WebGL app, you will basically come up with something similar. So we decided, okay, let's take at least that. It has nothing inside, so it's no batteries included, it's just a small wrapper around WebGL API, because WebGL API is low-level API. So if you are used to writing just JavaScript code, so it's similar like if you would write drivers for the computer. So it's up to you. All control is on you. So that's why it's not so easy and so pleasant sometimes. So that's the reason why we decided, we landed on it. And we chose this one because it was very small. So the engine, the wrapper itself was like, I think 10 kilobytes or something like that. So you'll probably not even see it in your code of your game. The second part, what we realized that we will not be able to use our same model structure what we used in Babylon, because specific formats for models will require some parsers, some loaders, and so on. So it's extra weight, it's extra seconds at start. So we ended up with just raw data in JSON. So that's it. So, and how we did it? We basically used the same tools. In our case, it was Xamarin's 3D editors. We exported the model, and then we made a script that just took the essentials out of it and added in our JSON document. At first, I was a bit worried about this because it was an extra step between designer and us, and we could mess up something. But in reality, it offered enough, and it was way, way smaller than our original files because it has no fancy features. So it just gives you pixel coordinates of your model on a screen to create a form, and the rest is up to you. Also, we stripped down all the duplicated data, so we had only one pattern and we duplicated everything in code. And yeah, spreadsheets. So you people know what spreadsheet is. So it's basically an image with small images inside. This is very important thing when you work with WebGL or in any GPU, because the most expensive thing what you can ask your computer to do is upload the image to the GPU. And imagine if you would have like 50, 60 small images, you would just constantly upload them up and down. So you would have constant context switching, so this would drastically decrease your performance and sometimes even crash your app on some of the devices. That's the reason why the spreadsheets are a crucial part if you want to optimize some on CC technologies. And not only WebGL, it's also the same for any AAA engine. So we came together with the designers. So of course they wanted AAA quality. Yeah, we said no. Bad for you. But we made a list of some minimum required features what we wanted to have a decent experience, because it's clear that we cannot deliver the same quality what we have in this first person, but we at least wanted to try to deliver as much as we can. So I will explain a bit. So this was a list. So we wanted to have lights due to the fact that otherwise, if you have no lights, you have no form, because that's how people see everything. So you see shadows and highlights on an object. Otherwise, sphere will be just a circle, not a sphere, if you don't have lights. Bad part, lights are the most expensive thing in any 3D engine. So if you will check some roadmaps of, I don't know, AAA studio engines, most of the time they say, we rewrite lights, we rewrite shadows, we improve shadows. And the reason is because the lights affect everything in your scene. So because like in the real world, so lights are casting shadows, they are affecting everything you give to them. So we made very quick dynamic lighting, very, very cheap one. For this who know, it's POM. It's the most cheapest, most oldest shading algorithm what you can implement. It's basically 5 lines of code. But we dropped it in the end because designers said it doesn't look as nice as it should. And what we did, we ended up just baking lights in our texture. So we assumed we will not have dynamic lights in our first apps. So we just added some highlight spots directly on the same texture what we use for models. So it's very cheap, very old technique, but it has its own drawbacks, of course. It means that if you rotate something, the light will rotate together with you. It will not be like real light. But we realized it looks quite nice, so we stayed with that. Next thing what our designers wanted, and hope you can see, this is reflection. So by the way, this is sphere on your left side, so without any shading. So as you see, it's just, as we were intending to make some realistic models a bit, so we needed reflection. Reflection is very simple, it's just basically in real world you see it on very glossy objects, like on the screens, on plastic, on metal, and without reflection you cannot make any metal material because of chrome, for example, because it's not possible, because that's how material works. You distinguish material from how they reflect light. So, for example, your mirror is perfect reflection, your chrome is maybe 50%, less than 50% reflection. At first I was scared because it looks very complex, but in reality, to implement reflection, all you need in your 3D world is just a cube map. I will show the next slide what cube map is. So basically it's a 360 image cut in 6 parts so that you can have a cube on your own. This one is spherical one, but we, for our engine needs, converted it to the 6-side cube. So basically you are sitting inside the cube. Of course, as you see, for example, this room is just a room, and that's by the way how games do it. So because real-time reflection from your real scene is quite a thing. It is doable, so if you will see maybe in very, very good hardware-based games, but in reality people just use some fake reflection maps that are approximately an environment where your game is located. For example, if you are in the wood, you will have some static wood reflection. So we did the same, so we just faked it. We implemented we didn't do as, for example, big frameworks do, so you have a static one central reflection what is applied to the whole game. We did it per object because it was much cheaper, as I mentioned. Our entry level is so low that if you would apply for all the objects, even if we don't need them, it would take extra resources. And how, I will probably not go in the implementation details, but basically you have, as I mentioned, this cube, you are inside, and then you just reflect array on the cube and see what's coming back, and that's your reflection. So if you are interested, the implemented shader code is 3 lines, to be honest. So it's very simple in the end, as long as you know the math behind it. So yeah, I removed the code because most of people are afraid when they see code in the browser. But yeah, so that's our reflection. And then we came to the animation. So this cube example, as I mentioned before, shader code is executed on GPU, so it's very, very, very cheap and very, very fast. So this is so we decided maybe we can utilize it for some animations. Of course, you cannot do everything there. As I mentioned, you don't have memory. You even don't know what's next to you. You just know that okay, this pixel is red because of things. So by the way, this is the minimalistic shader code. It just says that you have white, non-opaque pixel. So this is what shader code returns. So you can do whatever you want there in the shader. In the end, you need to return 4-digit array called vector 4, and it will represent your pixel. For this who know, yeah, okay, pixel is not correct term because there are pixels are divided in subpixels, but let's for simplicity assume that we are painting each pixel individually on the screen. We investigated it. We found some use cases. The best use cases are like this, where you have just color changes. So, for example, you have, I don't know, some gradient animation from one gradient to another. We even implemented it like that. So, but that's it. So that's it what you can achieve there. You can have mass there. So as long as you can describe it as a mass, you can animate in the shader. In our cases, we use it for example, for circle animations, for line animations, just to not have sprite sheet for that or any other code. Because otherwise you would need to make it manually, paint it, repaint it all the time. Shader is just executed there, you forget it. By the way, I will show the demos later, so it will be much more easier to understand why this is an important step. But this is one thing where you can save a lot of resources, especially low-time resources, because, for example, you can load some image and rotate it in the shader. It means that you can have more variety of the same image. So if you have, I don't know, buttons that is blue, yellow, and red, instead of having these images as separate images, you can have one template image, for example, like grayscale, whatever, how you choose it, and then paint it. So this is quite a nice technique, but also limited. Yeah. Okay. Here I probably will lose most of you, but this was the most important thing why we worked on Explorer 11. And here I will need to make a bit of break and explain a bit how WebGL renders. If you have used Canvas or maybe you have used some other 2D, 3D frameworks in browsers, you know that they are rendered constantly on records animation frame. So what happens in WebGL? In WebGL, same as in any animation, you have your loop that is rendered every frame, but inside you are looping through your objects. So imagine if you have this, I don't know, chessboard, let's call it chessboard, small piece of chessboard. So you have 4 on 4 grid. So if you will just create 4 on 4, or like 16 objects, you will execute 16 draw calls, so these painting orders each frame. For 16 objects, it's okay. I assume, let's assume you have 10,000. And this will, of course, slow you down. Your frames will get longer, you will get laggy, and so on. That's why this batch rendering, it has different naming. It is instancing, batch rendering. All it does, it groups objects and allows you to paint multiple objects at the same time. This was one of the main reasons why our games were capable of running on the Explorer 11 and still have decent performance and so on. Also running on lower level phones as well. So in theory it's very simple. In implementation it's a bit more trickier. Because yeah, it's nice. I want to render at the same time, but can I do it? Because if you have 10 unique objects, you'll probably not be able to do it. Because you can batch together objects only that are the same, or use the same shader, so the material. So, but for this specific case for chessboard, it's also possible to draw this chessboard on one mesh, so one plane object using shader. So, because you can divide the shader in X amount of columns, X amount of rows, find in which row your pixel is located, and paint that data. So, this example from chessboard was done in this way. So, you have one mesh, one shader, and you have very smart shader code that can pinpoint your location. Usually it's done using, for example, here it's very easy. You just divide your whole width and height by amount of rows and columns and just try to find your index, for example, index 1, 2, 3, 4, 5, 6, 7. But this works only, of course, with grid-based objects because otherwise you need some extra information. Yeah. But other way around, how you can do it, you can have one mesh, but you can draw inside one mesh multiple smaller ones. That's called instancing in DevGL. It's standard feature for most of frameworks. Our didn't have it, so we needed to implement it. So it means that you draw one. For example, each shell would be a one part of the mesh. You just draw it multiple times. That's other way around. So that's a bit better because that's done on CPU side, on your JavaScript code, so you have more control. So that means you can, for example, have positions not just linear, but also randomly positioned. But it's not as efficient as pure shader, of course. Okay, hopefully someone's still listening. So the last bit, this is the part that people usually doesn't suspect when they have performance problems. We noticed that when we are doing first-person gaming. So basically, we noticed that mouse move events are very expensive. And I will explain why. Because firstly, they are expensive on browser because of spamming a lot. Secondly, in 3D world, if you as it's just an image, as you imagine, just a canvas. So WebGL is basically a canvas with different context, with 3D context. So imagine you have 50 objects in your scene. So every time you move a mouse, you need to loop all the 50 objects. Let's assume all of them are interactive. So because if they would not be, you could very quickly filter out only these ones who are. But if all of them are interactive, every frame, every loop, you just go through all the objects and check if you have a hit. And that's why it's so expensive. Like, all depends. If you have simple animation, you will probably not notice any difference. But on bigger scenes, it's really getting in a way. So what we did, so to avoid all this, we basically checked our apps that as first generation of our apps were quite static. On next slide, you will see the demo. We just painted bounding boxes on the screens where you can click. That's it. So we had, I don't know, 10 bounding boxes, like 5 bounding boxes. You just check your mouse, okay, you are on. Right point, click, very cheap, done. And we don't care if it's sphere or anything, because just as long with this work only as long as you don't rotate your scene. Because as soon as you start to rotate, these boxes will be out of sync. Okay, and here you go. This will be one of our first 3D experience in live games. Let's see. So it's very simple, but nice and still very popular among our players. So what you see is a studio, and soon you will get a look on 3D overlay, what we applied on top. So yeah, we have command, we have aim, we have overlay for our studio screens, and all that stuff. So you can basically click, drag, drop, whatever you want. So, and yeah, you have nice, so small animations. If you ask me, of course, probably most people just laugh with because if you compare to AAA, it's basically nothing, of course. But 5 years ago, on that, all that low-level devices, this was quite a success, to be honest. And everyone was quite happy. Designers were maybe a bit pity because they didn't get all the nice dynamic lightnings and all that stuff running. But yeah, this was our first generation of engine. And if you take this game in particular, So as I remember, yeah, the whole engine was 20 kilobytes, and the whole game with all the assets and models was 500 kilobytes. So it was relatively small compared to what we got. And also most of the weight was coming from these sprite sheets. As you saw, these splash are just sprite animations, very small ones. But yeah, and kind of because round things need a lot of information to be round. This means if you have a round object, it will weigh a lot more than a square one, because square have more linear look, so it's enough with few points. In circle ones, the less points you have, of course, the more quadratic it will look. So if you take out canon and the textures, it's basically 50 kilobytes left, because rest is just pure code and a few sprite images there, and the rest of us is just shader code and so on. So that was our first generation of engine. So what are the conclusions? Works for very simple animations. We had fun building it for sure. We managed to run it on Explorer 11, so we added only a few polyfills because it made our lives easier, so we didn't need to rewrite it. And yeah, the data what I already mentioned. And by the way, these apps are still running on environments where most of other big frameworks are not, but it's clear why. Because they're simple, they're very small, and they are handmade basically, because the engine has nothing inside. As I mentioned, this is not an engine where you just can use and try out. If you want an object, you need to write shader for it on your own. So that's the part where it gets trickier, because not every, as you assume, not every developer in the company probably can write a shader and can do it. So this was, of course, a bit of bad part, but yeah, overall the experience was very nice. We didn't have like very big architectures there, so there were just objects floating around, but in the end, all worked and all was nice. So what's happened next? This is where things became even worse. So after this project, we had the next one, multiple ones. So in between projects, we decided to improve our engine, and then someone came and said, can we do a virtual reality game here? I said, yes, of course. You can just take Babylon.js, it has VR out of box, let's use it. Yeah, but there's a catch. It should work with the same code as a standard game. Yeah, great, that's not so nice, because as you remember, our low standards, it means again, no big frameworks with out-of-box support. The VR story is probably, I will not go very deep in it because it's a story on its own. So maybe some other time I will tell how it went. But as a bonus, we were doing it during COVID. So we were working from home. So we needed the logistics to have these devices delivered to the developers, designers, and all that. But what we, as this is engine talk, I will mostly focus what we needed to add to the engine and what we added on the second generation to support virtual reality. So main difference was that we could not use our simple input manager anymore, as you remember, because in virtual reality you can move around, and that's it. So we needed to go back to the real input manager, but that will have a slide and so on later a bit. We realized, yeah, that we need to improve our architecture, so we moved in a direction a bit similar to the other frameworks where we had this hierarchy, you have parent-child relationships, all that stuff. Probably, if you have used any gaming framework, you probably have used it already. And we standardized a lot, because otherwise the code was copied all the time and it was hard to maintain. And we added testing library so we can finally unit test our 3D apps. So what's next? So what's about this VR? Yeah, as I mentioned, our business wanted single base, so it means it's the same app what we have in a browser should work in VR. But there's a catch. In VR, you don't have DOM. As you saw, we had mixed reality app, we have video, we have WebGL, and we have our simple DOM UI as well. That was taken away, because as soon as you enter VR, immersive mode, you have only WebGL. It meant we need a UI framework for our games. And that was basically the biggest challenge. because the engine itself was so simple that we managed to add VR renderer very quickly, because the only difference was that you need to render it twice. One eye, second eye, that's it. Rest was working out of box. Other big change was input manager, but that we added quite relatively easily. Yeah, the biggest challenge was UI, because if you have tried to write a UI in non-DOM environment, non-markup environment, you probably know how hard it is, because there is no layout, there is no styling. So if you want it, you need to build it your own. I suggest to try to build some few button layout in the canvas at least to see how it works. But yeah, what we came up, so as we had no other option as to improve our framework, so we made a small UI library, because yeah, I will show a demo next slide. But basically it's just, we took some buttons, we draw them in the shaders, mostly, and yeah, the thickest part is the text. This is bad, because especially for us, as we are localized games and we are supporting a lot of markets, it's because you have a text on one line for one language and you have 3 lines of text for another language, so you need to be flexible there, so you need to, so this is why I would not suggest to write UIs in WebGL, but yeah, in this case we didn't have any option, because at the time of writing there was no other possibility to have it. Yeah, and so we upgraded our engine, so we added these small changes what I mentioned. The biggest change here as well was this shader standardization. So what we did, as shader is C code, it's just plain text basically. We just had some sort of chunks of shaders with chunk features, so you can include in your code. So that's basically what most of the frameworks do in our world, because it's in the end it's just a text. So all you can do is string replace or do some stuff like that. On a runtime, on a compile time, but that's it. Yeah, rest was just housekeeping for developers so they feel a bit more comfortable. But Armands will tell his experience, because this was, the VR game was his first full game in the company. I assume he has some strong words to say. So yeah, input management, this was also, I was very confused, because for me it was like, I assumed that frameworks do it already. But at the time of writing, there was not unified code for Babylon.js, for example. So if you added the input management for your standard games, it would not work in VR, because they didn't have any like common input controller. So you had touch events or pointer events for them and VR controllers. What we did, we made input management so that you get the same events for all the sources. So basically, that's the reason why our game was working in standard browser and VR directly, because all it changed is how you get data. You can get it from mouse, from touch, or from some controller. We even added some console controllers later for fun. Yeah. Okay, so this is our VR game. As I mentioned, yeah, it's not, of course, first-person shooter, but it was quite fun building it. It was meant as an experiment, so we don't have it live anymore, but anyway. As you see, we have these UIs there, we have chips, you have your betting spots, you have your video around you, and so on. Yeah. I really enjoyed it. Let's see, maybe in future we'll come back and we'll build more, but that's, I just get sick, by the way. I don't know how you get, but I could not play it more than 5 minutes. So imagine how its testing was going. Yeah. So yeah, so the game itself is playable online if you want to check, but not in VR mode anymore. So because we got our data, we got our feedback, we were happy with what we got, and we just, because imagine that yeah, you need to constantly support it. But we'll see. Yeah. We'll see in the future. Maybe we'll get back to it. So, conclusion. As I mentioned, don't do UIs, you'll never. Now, if you start from scratch, it's much easier, of course, because 3JS, Babylon have their own UI framework, so would not need to build them. It's still tricky to use them, but at least you would not need to build them anymore from scratch, because at that time when we were trying this out, the VR hype was not there yet, so there was not much tech available. Also, the issue was documentation, because everything was constantly changing. So you told one device works there, you take another brand, nothing works. Why? This is older. Okay. You need to support multiple apps and so on. So right now, if you build a VR game, it's just basically one button click, export, and done. So most of frameworks will support you, and if you don't have such, for example, maybe low entry points, if you can use whatever you want, and it's very, very straightforward. And by the way, video is not very good in VR mode as well, because of these two renderings, big assets. So you feel, even on the highest bandwidth and high resolutions, you still feel that it's lagging a bit about. It's no issue. It was known by browser vendors, but they said they cannot do anything. And at the time of writing, not all browsers even supported video in VR. There were vendors with Fruit label on it, so they didn't support it at all. So it was mainly from where you could play. But as for from the engine, we were very happy that we had very stable engine. We were having VR support very quickly, and by the way, that was one of the pluses. It was our engine; we could extend it very quickly. Okay, so Armand will tell about his experience now, and will tell how we went further from this point. So Armand.
So at Evolution, I first joined as an app developer, so my job was to create apps. And one day they decided, hey, do you want to try creating games? I said, sure, why not? Boom, your first game will be VR. So I had no experience with React, no experience with web, no experience with GL, so this is my first game. And yeah, it was quite scary, but as the engine was at that stage quite mature, it was quite easy to me to like build some UI, some like layouting stuff, and even check how things doing in under hood. So for me, it's quite easy to understand. But okay, next year, next challenges. As you guess, new version of the engine. There was a new idea from the business. Hey guys, do you want to create a slot in the live games? And the slot is interesting mechanic because it's like a 3D cylinder and they rotate. So the only option we have is WebGL. But this is the main component for the app. And there's a lot of major components in this app which requires WebGL. So we decided, hey, like the existing engine is okay, but with the previous experience, what we had to improve it. The most hardest part was how do we transfer data from the WebGL to the. So our React components had state management, so there was like easy just to connect the state management with the components in React. But WebGL we didn't have that. So the hardest part was to like deliver data back and through from WebGL to our state. So we tried, hey, maybe we can just take the same experience what we have in React and use it in WebGL. Why not? It will come with a lot of benefits. For example, we can use the same storybook support that we have in React. We can use for WebGL. And also all the state management stuff binding was like already fixed from like out of box if you use the same logic. So we decided, hey, let's take this. There's a library called React Controller, which allows you to create your own, basically, React tree. So we make our, like as you create divs, example, or I don't know, text or something like that, you can just create your custom meshes or objects. You just wrap them, and then you just write as the React components. So you can use hooks, you can use state bindings and so on, but instead of using divs, DOM elements, you're using WebGL elements. So it was, very interesting. So we just created our own solution for that. The benefits was that, you can create the same styles as you create your React components. Responsibility between WebGL DOM components was, the same. yeah, and you can easily test in a storybook. So this is the app what we have. So this is our slot, which is like rendered with the newest engines. Still use the same framework, works great. It doesn't matter if you use React or WebGL, it's just same style, same structure, same architecture, so works very well, I think. Of course, not everything was working like smoothly. So as I mentioned, the main selling point for us was the same APIs as React and the same database as React. So everyone who was like familiar with React can come in and like add some adjustments. But of course, there's some like limitations for that. First of all, you cannot mix DOM and WebGL elements in one tree. So they're basically living same different like lives. So you can I don't have like one under one and like above DOM and above WebGL and so on. You can't do that. There was an issue with mounting and unmounting because we are like in React, you can like you're used to like delete the components when you don't need them, but in WebGL it's a little bit trickier because it's very expensive to create one. So we have to be very careful how we manage the states and how we manage the components to have the performance. Yeah, it's harder to optimize rendering because in React you can just use CSS updates and everything will be better, but for WebGL it's quite complicated. And sometimes it gave a lot of headaches because we, for example, used hooks, but like for example, for animations, it would be easier just to create an element and animate it. But yeah, so we feel that some places there was extra complexity because we just wanted to feel like React. So overall summary for the whole experience was that we gained a lot of knowledge about WebGL because yeah, we had to create an engine ourselves, so we didn't rely on some already done frameworks, so you just, if you need it, you just make it. So it gave a lot of knowledge for us about WebGL, how it works. Also, it's like, it was only made for our needs, so we don't have any extra stuff which we didn't need, so it was very lightweight, and it was specifically made for our needs. So if something was not working as we should, we just created to work. Yeah, full control, easy to customize, and the performance also was great because yeah, we didn't include stuff that we didn't need, and we can optimize to like deepest details. The drawbacks. So the problem is that there's very hard to find engineers who have deep knowledge of WebGL. So if we need some maintainers, it's quite hard to find them. Also, full control engine is a great thing. At the same time, it's very quite like a drawback because if there's nothing there, you have to create it. So you have to create it and maintain it yourself. Yeah, all features need to add it manually, like lights and reflection, text support, anything which you may imagine. Yeah, it doesn't have this like, if you have used like the biggest like big frameworks, there's a lot of features over there like text support, image loading and so on. There's nothing, you just have to like add it. Yeah, as it's very hard to hire devs for that because it's very specific framework for our needs. So it's like an in-house framework. So we cannot just, hey, you have experience in Babel, just come in and work for us. It's just like, no, it's like customly made. So we can't just hire specific devs for that. Yeah, no external tools, extra tools for like testing and I don't know, some debugging and so on, which like has the major frameworks. And also, no, I cannot ask in forums, hey guys, I have this issue with this framework. No, it's your framework. There's nothing to ask somebody. So what's the current state? For now, we haven't added any kind of like extra improvement for this framework. So for current agreements, we have decided we will probably move some of the major frameworks. The reason was the requirement from designers and business was now grow very big, and like I think we just like easier to take some bigger frameworks instead of like adding stuff to the existing one. Also, the situation with the major frameworks also is better, like performance-wise and also like size-wise. So conclusion is that yeah, it was fun to make, very like useful for us. I think we learned a lot. It's yeah, it's lightweight because yeah, it doesn't have a lot of features. So yeah, as I mentioned already, we have like apps, newest apps, which has like very complex ideas, requirements. So it will be very hard to like add some, but we understand that the community support is very crucial because it's easier just to ask somebody, or maybe somebody has already implemented some features in specific frameworks. So it's just a little bit easier to work and a little bit faster to work like that. Also, it's easier to find developers who has experience in the major frameworks instead of like custom ones. Yeah. So if you need, like, if you have these specific requirements, then yeah, you can build one. But yeah, for now we will stick with the major ones. The main point is that if something is, you cannot do it, don't be afraid to just try it out and build yourself. That's perfectly fine. For example, VR, we didn't scare and we just, hey, let's build VR. Why not? So, yeah. I hope everybody's still awake. So yeah, it was a great journey, and I hope you got at least some idea and some like conclusion what we are doing in evolution. And yeah, thank you very much. Maybe any questions later? No?
I have a question.
Yeah.
How popular is VR in gaming?
Sorry?
How popular VR in gaming?
Not really. Our experiment was that there was interest, but yeah, it didn't go like really like majorly. So I think that the people and everyone had an interest of it, but like something which is like you know, for a long time I don't see that. No. I would say yeah, it just was an interesting factor. Then you just try out and that's it.
Can I?
Yeah.
So did the business drop the Internet Explorer 11 support requirement?
Yes.
And I guess another one is basically now from this standpoint, would you do it again, or would you choose the engine out of the market, maybe open source, and make it custom?
If we would need to do it now or,
Yeah,
or back then?
Once again, back then.
Once again, at that time, yes, because we had restriction on file sizes and so on, because we could not find any engine that was capable of that first generation support. Would we invest more in the VR and so on? Maybe no. I would probably try to maybe argue and make two different games, one for VR and one for non-VR. But at least the first generation, I would do it again, yes. Also, all the knowledge what we gain is transferable now to all the standard frameworks. So we are using the same approaches. We know what's happening under hood, so we can optimize even the same Babylon.js or 3.js, because it's not anymore some black box. We know exactly why it's slow or why it's doing like that.
Okay.
Yeah, the game with the cannon and spheres being heavy and the cannon itself being like 400 kilobytes. What about making a design choice and maybe the cannon could be a toaster, something square?
The theme of the game was circles, so.
Circles.
But yeah, this is the thing. So the rounder the element, the heavier it is. But there are options. So if you would do it, maybe if you would want to invest more time, you could have half of the element loaded and then mirrored it. It doesn't work always, it works with symmetrical objects. It didn't work in our case, but in case you need it, it's also possible. But yeah.
And one more small
Yeah,
question.
sure.
Have you considered pre-rendering like majority of those scenes? Because yeah, when you can turn your head, that's hard, sure. But for the ones where you can't turn your head, I think some of them don't allow for it, right? Is it, have you considered pre-rendering this and then just adding dynamic objects to the scene later on and calling it quits from there?
You mean pre-render?
Pre-rendering, I mean just do the image texture instead and
Yeah,
Instead of objects.
most of you see in the first generation especially was already pre-rendered shadows, lights, all the objects. The only part what was basically really dynamic was the cannon in the game. And of course, it would be possible, we did that in Flash times, these who know what Flash is. You can pre-render 3D objects from different perspectives and use a sprite sheet, but it's super heavy. So I think the last time I used the technique, it was a few megabytes just for one object because you need up, down, left, right, and so on. Yeah. But technically, of course, you can even have 3D effect without 3D, but it's very, very heavy. Much heavier.
And the sprites, do you still manage them yourself? Do you put them together yourself, or do you have some compilation pipeline that puts all together?
We have, yeah. So basically, we export some images, and then we can make sprite sheets out of them. But also, we can have some restrictions, so we can have multiple of them or one big. Depends on how many you have. But yeah, we have a pipeline for that. Just.
Yeah, if evolution is leaning towards like new approaches and not using some internal framework, maybe anyone considered to make it open source? But like if nobody ever use it inside, maybe it could be something beneficial for the others. Just take a look how you did it.
We sometimes consider this. It's not like we don't use it, we don't invest anymore, at the moment at least. Because it's as good as it is, and we stick with it. We still use it for small apps. So if you have very small, like one object app, then it makes no sense to go for the big framework. But sometimes we consider it.
But this engine is still used in our games, so we are not just not investing in new games. This one, so we still have games which use the first version, second version, and so on. So. Yeah.
Was the version management hard? Like, how do you ever upgrade the engine made of the old version to the new one?
Yeah, so when we're creating the second framework, we just save the first version and then like create a separate. The second version was completely like rewrite from the first one. And the third version was just as an addition of the second one. So for one while, we have just two versions. They're like two separate projects, let's say. But in general, we deprecate the first one and rewrite everything to the second one. So we have at least one in the end.
How do you manage creating of, like, there are projects, right, you need to deliver those games. How do you port features back into the core, or do you just copy features, or do you do them in the core first? What's your approach here?
It depends on the situation. So this case was very specific because first version was basically non-compatible with second one. But usually we try to build something, use something, and then we just check, okay, if we see something maybe what others will use, then we move to core. If not, we just leave in the project because it's easier to adapt. Because as soon as you move to core, you need to support it not just for you, but for everyone in the company, and that's of course a bit different story. But there are features that are directly created in the core because we know in advance, for example, that this feature anyway, because it's usually the engine features or something that is globally necessary for the whole company.
If you have some more questions, please come in person. Guys will be here for 3 minutes. No, for some more minutes. So let's go on a break now. Thank you.